In this video, we'll talk about compound interest in terms of creating equations for exponential functions. Now, it goes beyond just money, just beyond banking, just beyond marketing. You can use this to create just about any kind of exponential equation. It applies to exponential decay, it applies to growth, it applies to population, it applies to radioactive decay, all those things. So this is a very useful formula. So let's talk about the formula. So usually we think about it in terms of money. However, as I mentioned before, it can be applied to any situation where exponential growth is applicable. So anytime we're talking about money here, we can also assume that could be talking about bacteria, that could be talking about whatever. So let's go ahead and start with A. A is the amount of whatever, usually when we're talking about money, so amount at the end. So it could be money, could be population, could be whatever. Okay, P, this is what is usually referred to as the principal, and that is like a financial term. Basically what this means is your initial amount. So the amount of money you have to start with, the amount of population you have to start with, the amount of whatever you have at the beginning, at t equals 0. Okay? While we're talking about t, let's define what t is. T is time in years, usually. However, if we're talking about growth of bacteria, it makes sense to probably do days or hours even. So it can be years. Usually we talk about it as years, but it doesn't always have to be years. So long as you're very careful with the rest of your formula, you can make it not years. Okay? R is your growth rate or your decay rate, if necessary. So this would be usually a percentage that you turn into a decimal. So if it's 3%, it's 0.03. And we'll do an example to kind of illustrate this. And then lastly, we have N. And it shows up in 2 spots in this thing. And sometimes it's a factor and sometimes it's not. So this would be the number of times that your money is compounded in a year. And this is usually one you will only see with money. If we're talking about population, usually we don't worry about N. So like for instance, if instead of my bank calculating my interest once a year, they do it twice a year, well then N would be 2 in that case. Or if it's quarterly, it's 4 times a year. If it's monthly, it's 12 times a year. If it's daily, it's 365 times a year, so on and so forth. And we could run that N out as much as we want. Usually, it's pretty common you'll see annually or quarterly. Those are usually the big 2. So let's look at an example where we are talking about money. We have a bunch of information given to us. If we invest $5,000 for 7 years at 3.2% interest compounded quarterly, we want to know how much money there will be at the end. And I find the best way to do these is just literally list out your variables. So we got A, we got P, we have N, R, and T. And the idea is we want to figure out, we're just making our list, we're figuring out what we want to know, and we're figuring out what we have. So what we really want to know is we want to know how much will be at the end. So A is what I don't know in this case. Okay. Now, likewise, I'm looking up here. $5,000 is invested. That tells me that's my initial amount. That's what I start with. That's P. Okay? I'm looking at 7 years. So 7, okay, probably is going to be where T is. 3.2%, that's would be my R. That's my growth rate. So 0.032. And then N is kind of sneaky in here. It's compounded quarterly. That tells me 4 times a year we're going to compound interest, and then I'll gain more interest on that little bit of interest I had, let's say in 8 months. I'll have 2 chances for that. So N in this case is 4. And then we just roll with our formula. And we're going to plug in what we've got. So our formula is A equals P times 1 plus R over N to the power of NT. Now, let's just plug in what we know. We don't know A. So A is going to equal whatever. 5,000 times 1 plus R, which in this case is 0.032, divided by N, which is 4, to the power of 4 times 7, because that's our T. And now we just simplify as much as we can. So just taking a step here, I'm going to leave the 5,000 alone for a second. I'm going to simplify this piece in here. This will be 1.008, and then 4 times 7 makes 28. At this point, I'll run to the calculator. I'll do 1.08 or 1.008 to the power of 28, and then I'll multiply that by 5,000. And if I do that, I get 6,249.782497, roughly. Now, since we're usually talking about money, we're talking about banks. Banks normally hold on to that extra bit, so they will just literally chop off that little bit and keep that for themselves. So when I'm asking as a math problem, I can see an argument for rounding up possibly, but usually when we're talking about money, we just chop it right off. So you're going to have $6,249.78. That would be the amount at the end. Now, I think this would be much simpler than trying to take a fraction of a percent, doing that 4 times for 1 year, and then repeating that process 7 times until we get to this number. And even then, it probably wouldn't be that number because you have to make an estimate at some point. So this is as close to it as we can be, being as exact as possible for as long as possible. So let's change gears here. Let's actually talk about an example that's not money, just to show you that you can apply this formula to something else. So let's say we have bacteria growing on a dish. Initially, there are 10 bacterium, that's plural for bacteria, and they will grow by 30% each hour, and I want to know how many there will be in 1 day. So in this case, it's not quite perfect because we're not allowing for continuous growth here. We're making the assumption that every hour, instantly, we pop out a bunch more bacteria. And then another hour goes by, we pop out a bunch more bacteria, and it's not a continuous process. So this isn't perfect, but it can work. So let's highlight some important information. Probably the starting 10 would be good. This 30% is good to know, and that's each hour. And I want to know how much there's going to be after 1 day. Now, in this case, I don't think we need to worry about N. So we're just going to not write it down. We have A, we have P, we have R, and we have T. So ultimately, again, we want to know what A is. All right, that one's pretty easy. Initially, we start with 10 bacterium. Okay, we know the growth rate is 30%, which is 0.3, and 1 day. Now, we have to be careful. This growth rate is based in hours. So that means I also need T to depend on hours. So instead of 1 day, I'm going to write 24 hours, which is also 1 day. So we just have to be very careful that our units are consistent with our rate. So this is a case where T may not be years. Now, usually we talk about it in money because we talk about growth in terms of years usually. And now we run to our formula, and we start plugging stuff in. So A is going to equal 10 times 1 plus 0.3 to the power of 24. Keep in mind there's no N here. So in this case, we can assume N is 1. We just don't worry about it. So now we can do some simplification. A is going to equal 10 to the power of 1.3 to the power of 24. Which if we do that, we will get A is going to equal 5,428.007704 bacterium. So the idea being we probably don't have a fractional bacteria. So we can just say it's 5,428. Now that's one example that doesn't pertain to money where we can use compound interest.